Hello, Ecotopians. I was hoping this lecture recording would be short, but as I got into it, it got longer and longer, and I'm sorry. And it also doesn't have a lot of bells and whistles, like pretty pictures and funny things in it. It's very text heavy, so it threatens to be a little bit boring. Hopefully, it won't be. Try to keep it going, but you better belt up and buckle down and pay attention so we can get through this. What this is all about is hypothesis testing. That's what it says, and it's designed to help you approach your very first science experiment, not experiment, your science assignment, which is creating a testable hypothesis. What made it long was that as I started thinking about it, there were a number of words and concepts that were essential that everybody understand. We all have to get on the same page with these words, and they turned out to be a little bit more complicated than I thought. Well, let's dig into it and see what we got here. Here are the concepts and definitions that I wanted to clean up. First was understanding the nature of certainty and uncertainty in science. Many people believe that science is there to provide certainty about stuff when the opposite is exactly true. I'll explain that in a moment. Also, this concept of proof and the concept of theory. I want to make sure we have a common understanding of what those words mean within the scientific context. Okay, so go back and remember we covered critical thinking in a previous lecture, and one aspect of it was always being open to new ideas or ideas that challenge your own. Having an open mind, that is a essential part of critical thinking. Science has embraced critical thinking, and so science are always open to new ideas or ideas that challenge their own, ideally. So ideally, there is no proof in science. There is just support or a lack of support for an idea. So that might come as a surprise to many people. You think, well, you use science to prove stuff, right? Actually, no, you use science to disprove stuff. And by disproving enough stuff, we arrive at the truth in a really ironic, surprising way. No proof. There's just support or lack of support for an idea. Okay, but what do we say when there's overwhelming support for an idea like there is for the germ theory of disease? Many diseases seem to be caused by germs, or evolution, which there's a lot of evidence that evolution is the way diversity of species happen, continental drift, or anthropogenic climate change. Don't we say that these things are now proven? No, we don't. We remain open minded, but we do say is that these are now theories. Wait a minute. A common understanding of the word theory is that it's a wild idea, an unsupported hypothesis, a guess. Oh, that's just a theory. You're just theorizing. That's not true. It's just a theory. But what it means in science is that the word theory is a hypothesis that has withstood the strongest challenges that scientists could assemble, and thus, by consensus, it has been accepted as the truth by the vast majority of scientists. Wow, that's crazy because that's the exact opposite of the common understanding.
Got very good arms.
He didn't fall? Inconceivable. You keep using the word. I do not think it means what you think it means.
Let me just give you some examples of scientific theory. The earth is round, not flat. That's a theory because it has withstood a gazillion tests to prove it wrong. Nope, the flat earth hypothesis has been proven wrong. The earth rotates around the sun, a Copernican revolution. The theory of gravitation. I'm not quite sure. I was going to give Isaac Newton credit for that. He devised the equations that explain gravitation, but I don't think he understood gravitation. That had to wait for a while. I think it had to wait till Einstein came around and explained relativity. So the theory of relativity is another one. Really good hypothesis for how the world works. So good we can do things like drop nuclear bombs on Hiroshima and Nagasaki. Unfortunately, yeah, the relativity helped us understand making nuclear bombs and other stuff. Evolutionary theories I talked about before, and anthropogenic climate change. I threw those last two in there because they remain somewhat controversial today. There's not much controversy over the shape of the Earth. It is not flat. But I'll just let you know from my point of view as a practicing scientist of many decades, the evolutionary theory and anthropogenic climate change are very strongly supported by the vast majority of experiments, and the vast majority of scientists accept them as a theory. So, in science, there is no certainty, nothing is ever proven, but super well supported hypotheses are accepted by almost all, and these are called theories. Okay, I hope we're on the same page now. When I say theory, I hope you know what I mean. A super well supported hypothesis. It's a good working plan to accept them as the truth. Although, since I'm a critical thinker, they could all be turned over with new evidence. I'm open minded to that. Regarding uncertainty, scientists embrace it. And the coolest trick they use is to quantify their uncertainty about stuff. Here are some examples of questions scientists will never know the answer to, but which they can quantify their uncertainty about. Sorry, Mom. My mom would say, but about which they can quantify their uncertainty. Shout out to Mom. Okay, how many people are there in the United States? Well, nobody knows exactly how many people are in the US right now, or now, or now, or not, because it keeps changing. Some people die, some people are born, some people immigrate, some people emigrate. It's a constantly fluctuating number. But we can have estimates, and the estimates can have confidence intervals. 95% sure that the number of people in the United States right now is between these two numbers. Want to get that confidence interval narrower? Give me more money, and I will come up with a more rigorous sampling scheme to model that. Here's another one. How much antibiotics should a person take, and for how long? Well, for what disease? And which person? Male, female? What age? How large are they? For every person who's a certain gender and age and size with a disease, it's possible that there's uncertainty about how much they should take there. But if we minimize the uncertainty without attaining certainty, we can come up with a good prescription for people, and usually, well, hopefully, usually make them better. How strong is an I-beam? An I-beam is that thing you put down to support a bridge or whatever. How strong is it? Well, not all I-beams are identical. There's inevitable variation in how they're produced and what materials are in them and whatever. And they break at certain, like, some will break at this, some will break at that. So the strength of an I-beam can say is 95%. We know its failure rate with 95% certainty between this and this many kilograms. So you want to have a narrow uncertainty, but they'll never be certain about how strong any I-beam is. How many polar bears are left? That's even harder than figuring out how many people are in the United States, because polar bears don't fill out census forms. This is a really complicated one and super important. How much carbon dioxide does California emit every year? And you see these estimates all the time in the newspaper. If you read the newspaper, which I hope you do, it's really important for climate change and for policy for states and governments to know how much carbon dioxide they're emitting. We really got to understand that. And so we try very much, but we never will know exactly how much we emit. All we have is how uncertain we are, an estimate with uncertainty. How about this one? Is it better to travel from Arcata to Eureka via Highway 101 or to take Highway 255 past Manila? I wonder if you know where I'm talking about. If you drive from Arcata to Eureka, you basically have two routes. One is go straight down the 101, or go around the north of Humboldt Bay over to Manila and the Samoa Peninsula and take a left right before Samoa and cross the bridges and go back to Eureka. There's two different ways. Now, here's the story. A few years back, I had kids. My children were rowing for the Humboldt Bay Rowing Association, and that meant that I was carpooling and I drove about 6 million times back and forth between Arcata and the boathouse in Eureka. And there's this sort of running joke among the kids, which is the better way to go, down the 101 or take 255? And half the students would go one way and half the students would go the other way. And one day one of the students said, well, my phone says it's faster to take the 101. And I went ballistic. Oh, stupid millennial Gen X telephone people. The truth doesn't come from your phone. The truth comes from science, and we have a way to figure this out. So I got all nerdy about it, and I started timing the trip from the point I picked the kids up to the point I dropped them off. And I did that a bunch of times, and as a nerd, I charted it out, I calculated some stuff, and I'm going to share that information with you as an example of hypothesis testing and also some tricky ways of presenting data. Okay, so here is the first chart. Drive time from Arcata to Eureka via two different routes, via 101, via 255. Oh, it looks like it takes longer to go by the 101. Wow, but people, don't you ever believe anything you see until you thoroughly looked at what's on the graph and thought about it. Let's take a closer look at this chart. Drive time, Arcata to Eureka via two different routes. What's this say over here? Average drive time in seconds. Oh, okay. So to go via 101, it's like 830 seconds, and to go via 250, it's 800. So the difference is about 30 seconds out of 80. And look, why did Murph start this at 780? He's trying to exaggerate the difference between these two. What if we'd made this chart starting at 0? What would it look like? This is what it would look like. I kept the old one here that showed the big difference, and over here it starts at 0, and here we are between 800 and 830, and now it's a different kind of look. Now it doesn't. It looks like there's it's slightly longer to go via the 101, but people, this is not drive time, this is average drive time. That's a mistake in the axis label. Don't it's quite possible that many of you have not taken statistics. If you have taken statistics, you know what's going on here. A difference in two averages does not necessarily mean there's a insignificant difference between these two groups. It could be there's a lot of reasons why there might be a slight difference between two averages. Maybe I only sampled twice going to 101 and I sampled twice going to 255, and there's a traffic wreck on the day that I went this way. So a better way, there's two ways to present this data that's more revealing, which is instead of putting in the averages, just put in all the data you got. So that's what this shows. This graph shows every dot here is a trip, and this is via 255 and this is via 101, and this is much more revealing. It shows that, yeah, it does look like maybe on average it's slightly longer to go by 101, but many times I went by a 101, I got there sooner than other times that I took 255. So it's not really clear. If I'm feeling lucky, maybe I'll go down 101 and I'll get there sooner if the traffic is slow. The other thing is, it looks like there's more variation if you go down 101, and there's several stoplights. And I think that's the main difference between the two routes, except for distance, is that they're stoplights. So if you get unlucky with stoplights, or if this is a really long one, maybe there's an accident or there's construction, I don't know. Something happened here. Whereas this way, there's really a lot of consistency going via 255. Another way, if you did take statistics and you learn how to do standard deviation of showing this data, is to put in standard deviation bars, average drive time, Arcata Eureka via two different routes with one standard deviation error bars. This again shows the averages at the top of the bars, but these error bars give you the variation. They show you the variation between the two routes, and you see that, you know what, when it's said this way, there's a lot of overlap between these two ways. Okay, why am I telling you all this stuff? Because I guess I was talking about certainty and uncertainty. It's not certain which way is better, but I have a better sense of how uncertain I am about the answer. It looks like maybe that it's better to go via 255, but not definitely. You might get lucky, and if you take the 101, if I did more sampling, if I went at different times, if I left from different parts of Arcata and had different routes, I might get very different results. But doing it this way, I now have a pretty good idea of what my chances are of getting there earlier, one way or the other. Okay, so we can never be certain of anything, but we can know how uncertain we are about a lot of things, and that's very powerful to know how uncertain we are about a lot of things. I hope you think about that. That's really important, and I think it's different from the way a lot of people think. A lot of people are seeking certainty. They just want to know. But that is not how science works. Science comes to know things by understanding how uncertain they are about stuff. Kind of surprising, and it's a very powerful approach. Okay, quick review. There's no certainty in science, just quantifying uncertainty. There's no proof in science, just amassing evidence to support a hypothesis, idea, or a theory. Always keeping open to the idea of disproof. And the word theory in science is something that about as close to proven as can be in science. So our theories were really strong hypotheses. They're probably true, but you never know. There have been scientific revolutions before where theories, long-standing theories, have been overturned. And it will happen again in the future, no doubt. So be very careful when you hear words prove or certain or theory. When you use the word, make sure you know what it means. And when someone else uses it, don't be too sure they know what it means. So when they say that, you're like, I wonder what they mean when they say that word. Okay, so and I'm putting these up here because also these are like, I'm emphasizing them, and that should signal to you test questions. I'm going to be testing you on your understanding of the words that I presented in this video. New color. Okay, so finally, hypothesis testing. What's a hypothesis? It's a statement of proposed truth. It can be an educated guess, it can be a wild idea, or a conjecture based on prior observation, or a conjecture based on logic alone. I'm going to give you some examples. Bacteria cause disease. It's a statement of proposed truth. Not all bacteria cause disease, and not all disease is caused by bacteria, but some bacteria cause some disease is my understanding. That's my hypothesis. Antibiotics kill bacteria. Okay, like this particular antibiotic, I think it kills a bacterium. That's a hypothesis until I've shown you evidence for it. I don't know if you'd believe it. There is life on Mars. What's the evidence? Humans have souls, but dogs don't. Okay. If you say so, even I'm not even going to believe you even if you do say so. I want to see some evidence. That smudge on Dr. Watson's pants cuff is the same color and consistency as the mud at the 14th Street construction zone. So he must have come from there. That's a statement based on logic alone and some observations. Okay, they're all hypotheses. They're not necessarily good hypotheses or bad hypotheses. They're just hypotheses. They're statements of proposed truth. Okay, so Now, there are good hypotheses and there are bad hypotheses, and I hope you're paying attention because your job is to come up with a good hypothesis and not a bad hypothesis. By the way, the last E here, if it's an E, it's plural. If it's an I, it's singular. So one hypothesis, two hypotheses. Please try to spell correctly. So what's a good hypothesis? Well, it's logical and it's testable. So it's not necessarily about something important. You might think a good hypothesis is only something that's going to lead to a further understanding of the development of the cutting edge of science. No, it's just, it's not necessarily about something important, interesting, or useful. It's something that's logical and testable. This is my definition. This is how I'm going to judge goodness and badness for this class. Practically speaking, if you want to get money to test a hypothesis, it might have to be something important, interesting, or useful, because why else would someone give you money for it? But in just the pure Platonic ideal of the scientific method, I will only be looking for logical and testable hypotheses to classify them as good. So a bad hypothesis is not testable or doesn't make sense, and I wanted to show you some examples of bad hypotheses so you know what I'm talking about. For instance, not testable. There is a ghost in my closet. If you think there's a ghost in your closet, maybe there's a ghost in your closet, but I wouldn't know how to test for that because I don't know how to test for ghosts. If you open the door and there's a spooky thing there that you can pass your hand through, I guess that might be a ghost. If there's nothing there, the ghost might still be there, but I just can't see it. I just don't know how to test for ghosts, so I would say bad hypothesis. God exists or doesn't exist. I don't know how you could scientifically test for the presence or absence of God. What is God? And since God does not appear to us stomping around on earth doing miracles all the time, so we can point and say that right there is God, it makes it really difficult. But not seeing that stomping around God doesn't mean there's not a God that created the heavens and earth. It's just that we don't have the means for testing scientifically, quantitatively, as far as I know, the presence or absence of God. If you can think of a way, please share it with me. I have a soul. I have not heard of how you can actually weigh a soul or measure a soul, so I don't scientifically can't really test the presence or absence of a soul or not. Or maybe it's not logical. A hypothesis might not be logical. Like this: if I drive faster, then I'll get better grades. I do not see the connection. Now, maybe in your background material, you could lay out the logic more carefully. I can't imagine how that would be done in this case, but I'm just giving you an example of something that's not readily apparent that this is a logical hypothesis. Or maybe your hypothesis is too ambitious and therefore not testable from a practical sense. And for the purposes of our class, practical means you can do it. It might be that you could design a better fusion reactor if you had $12 billion and you have a hypothesis for doing that, but you don't have $12 billion, I'm pretty sure. And so I'm going to be looking at this ambitiousness from the point of view of a college student. So here's an example of too ambitious. People from different countries prefer brown mustard more than yellow mustard on the most popular condiment requiring food in their neighboring countries. I don't know. Even if I had a lot of money, how would you figure that out? You'd have to do some surveys. You'd have to see about people's purchasing habits in different countries. So you'd have to do this in a lot of different countries. You'd have to figure out what is the most popular condiment requiring food. What is it? Like hamburgers, hot dogs, shawarma? I don't know. In their neighboring countries. So this is going to be too big, I think, for you and me, and so not testable from a practical sense. Bad hypothesis. Okay, more bad hypotheses. Too many variables. What do I mean by that? Best to show you by example. Here's a hypothesis that has too many variables. People with degrees in science and who part their hair on the left, or who are bald, or who don't part their hair at all, get along better with people with degrees in the humanities who have no tattoos larger than a silver dollar. But if they live on farms, they get along better with social scientists who are older than they are. Wow. I'm going to have another lecture on variables and how to pare them down to make a simple experiment. Um, it's best when you design your hypothesis that you minimize the number of variables and just do the best you can when you come up with your hypothesis to do that. Keep it simple. When you do this, it's just too hard to do. Now, in complete honesty, there's a whole field of experimental design and statistics called multivariable analysis that helps you design experiments with a lot of different variables in them, especially good in fields like ecology, where there's inevitably a lot of variables involved. For you and me, we're going to keep this simple and try to keep the number of variables maybe down to only one thing that's varied, or maybe two. I think actually I have it. Yeah, this actually happened. I had a student who said that this was her hypothesis. Plants that are kept warmer and listen to hard rock and roll will do better than plants that are kept cooler and listen to classical music. It's actually not a terrible hypothesis. She had a bunch of plants that were kept warmer and exposed to hard rock and roll, and another group of plants that were kept cooler and they listened to classical music. They were broadcast. She played music to them. They didn't turn it on themselves. And if there was a response that this group did worse than this group, how would you attribute what caused that? Was it the warmness? Was it the music? Or was it the interaction of the warmness and the music? Or not? It just was too many variables. If I'd be more interested in seeing if you could compare warm to cool, if that has an effect, or one kind of music versus another kind of music, if that had an effect. But mixing variables makes it, in my opinion, for this class, a bad hypothesis. And so that's what I will be looking for in your hypotheses. Okay, a common denominator among bad hypotheses, that should be an E, among bad hypotheses is that they can't be measured, or they can't be measured easily. Okay, so make sure whatever you are doing will yield a measurable result. And by measurable, I mean you can put numbers to it, actual numbers. Talk more about that later. So a good hypothesis is a statement of suspected truth which is logical and can be measured. Null. Okay, great. We're almost done here. We're getting down to the bread and butter of this whole thing. The null versus the alternate hypothesis. Now, here's the deal. You have to understand what these mean. And you're going to, when you submit your hypotheses, give me both a null and an alternate hypothesis, which is why you need to understand what they mean. Here's how it works. Every proposal for how the world works has its counter proposal. For instance, there's the positive, this is true statement. There's an opposite, that is not true. Okay, so that's kind of where we're coming from with this concept of null versus alternate hypothesis. Scientists are ever the skeptics, and so they embrace at first the not true statement. This is not true. What? So here's a typical sciencey point of view. No, it ain't true. Skeptical. The sky is not blue because of this idea you have. There is no difference between the two routes from Arcata to Eureka. Your new antibiotic will not cure dysentery. No, no, no. That's the initial approach to a hypothesis, is to take the null or negative point of view. A statement of no effect. But what you probably want to do, this is natural, you want to do is prove your cool, crazy idea. Some insight happened and you have an idea that this is true. In science, that's not, hold that thought and then reverse it and instead disprove the opposite. Don't prove your cool, crazy idea, disprove its opposite. So instead of there is an ideal amount of baking powder to use to maximize the fluffiness of my cookies. That's a perfectly reasonable idea, and it's probably obviously true. I know what baking powder is. It's a leavening agent. It causes bubbles when heated up, and that causes fluffiness in cookies. If you don't put any in, you're going to get flat cookies. If you put a whole bunch in, something terrible is going to happen. But instead of trying to prove this statement, you disprove the opposite. What will be the opposite? The null hypothesis will state it doesn't matter how much baking powder I use. All my cookies will have equal fluffiness no matter what I do. When set up that way, you can see right away, I hope, how easily you could disprove this. I'm going to cook 3 batches of cookies. One, I'm not going to put in any baking powder. One, I'm going to put the recipe's amount of baking powder, and another, I'm going to put 10 times the amount of baking powder. And I will show you, I'll do it, that there is an ideal amount of baking powder. I would actually do it more carefully and make more minor variations among baking powder. The point is that you understand what a null hypothesis is and get into the habit of thinking about that. Come up with a crazy idea and then state the null hypothesis, which is that there's no effect or it doesn't work. So now what you want to ask yourself in regard to these hypotheses is it a, well, I'm going to ask you about the cookie thing. Is this a good hypothesis? I think this null hypothesis is good. I think it's logical. I sort of explained it to you already, and the measurable part of it is after I'm done with my cookies, I'm looking at fluffiness. So I guess, I don't know, what is fluffiness? Let's say how much it raises, how thick the cookie is in the end. If I do things really carefully, I can then maybe cut the cookies in half and measure how the highest point of each cookie, and then do that for all those cookies and come up with an average and compare the average of this group to that group. Okay, so anyway, yes, it leads to a measurable experiment. So it seems like a good hypothesis, it's logical, and it leads to a measurable experiment. Okay, that's what you should be aiming for in your first science assignment. Okay, your testable hypothesis, that's what it is. Your job is to devise a good hypothesis. It must be logical and testable and doable by you and have a null and alternate hypothesis. Later on, you'll design an experiment to test it, although you won't have to run the experiment. I think I've explained before that now you don't have to run experiments and write them all up. It really reduces the amount of work both of us have to do for this part, and hopefully gets across important aspects of the scientific method to you. And also, I'm going to just say, it's advice. Try to make it a hypothesis you might actually want to test. You'll have more fun that way. You might actually do it like I did this thing back and forth to Eureka. That was really fun for me. And if you come up with something that's fun for you, then bully for you. It'll be fun. You'll do it and maybe learn something. That's my advice anyway. You don't have to do it, but why not? What should I do it on? What should you do your project on? I get a lot of students. I'm not a sciencey person. I don't know what to do. Nah, yes, you can. It's not a problem. It doesn't matter what you do. Don't try to impress me. Don't try to, you don't really have to learn anything new. You can if you want to. Just look for something. The kitchen is a great place to do experiments. There's all kinds of things you can do in the kitchen. So is your garage or your backyard or your beach. Wander around in these places that you like to go and just look for ideas. Look around and think, what is interesting out there? How can I explain something I see? Why are there so many bugs here? Are there more of this kind of bug than that kind of bug? Or this kind of plant or that kind of plant? Or what? Or maybe you already have a question about something. How can you find out an answer? Maybe there's something that's been bugging you for years. As simple as, like, is it better to go to Eureka that way or that way? And here's some examples. And by the way, I don't think you should do, I guess you can if you want to look at my examples and devise a hypothesis on them. you can do it. Kind of not cool, but it would be okay. Like I'm not really specific here, so it's cool. Experiments with baking cookies or bread or whatever, hamburgers, boiling water. Like what about boiling water? I don't know if you add salt to water, does it change the temperature of the water, or how long it takes to boil, or how long it takes to evaporate? How about what are these things that dissolve? Do they dissolve at the same rate? Does it really matter how inflated my car or bike tires are to gas mileage, or maybe to how long it takes you to bicycle somewhere if you're a bicyclist? Please be safe. Don't like overinflate or underinflate your car tires by crazy. Not my fault if you get in a wreck. Don't get in a wreck. How long does it take me to get ready every morning? Or is there a difference between how long it takes me and how long it takes my spouse to get ready every morning? Which bounce is better, a golf ball, a tennis ball, or basketball? What is better? How are we going to measure that? You can do it. This is a good one. This sounds like fun. Here's a hypothesis. My friend's ability to distinguish cheap wine from inexpensive wine, they're all the same. Everybody's ability is just the same. If you can figure out a way to quantify that, you've got a really good experiment. All right. You could try to quantify the number of cars on the road at particular places at different times. A null hypothesis would be there's no difference in the number of cars at this intersection in the morning versus these other times. Go out there and measure that somehow. Just a few examples. I hope you can come up with better ideas than I have, or not. It doesn't matter. Just come up with a good hypothesis. So, quick review and then some practice test questions. Here are some dangerous words: proof, theory, certainty, hypothesis. Make sure you understand them and how they're important to science. Here are some potential test questions. From a scientific point of view, is this a good or a bad statement? Einstein proved the theory of relativity. Bad. There is no proof. No such thing as proof. From a scientific point of view, is this a good or a bad statement? Scientists have not proven that evolution happens or that climate change is caused by humans. I think that's good because they don't prove anything. Okay, good. They got a lot of evidence. It's a theory now, but there's no proof. We don't talk about proof. There's overwhelming support for the theory of continental drift. That's okay. I happen to know, I'll let you know that is true. There is overwhelming support for, yes, this is a theory of continental drift. Good. Continental drift is just a hypothesis. Well, you know what? The implication of that statement is that it's just a hypothesis, suggests that it's an idea, it's a crazy idea, there's not a lot of evidence for it, and that's false. It is a hypothesis. In fact, it is just a hypothesis, but it's a very strongly supported one. It's now a theory. So I would say that would be a bad statement, just because of the tone of voice. Evolution is just a theory, so it doesn't make sense to believe in it. That is wrong. Evolution is a theory. That means there's a strong support for it over many years, gazillions of experiments that support how it works, and it's logical, etc. So that's a bad statement. Oops. Scientists are now certain, well, nope, that the universe began. No, they're not certain of anything, but they've got they've narrowed the range of uncertainty in that. It's about 14 billion years ago. Scientists are uncertain about their estimate of the age of the universe. That is true, but I wonder what the degree of their uncertainty is. My hypothesis is that sugar reduces that sensation of hunger more rapidly than do potato chips. Well, that seems like a good hypothesis, but I'm going to say that's bad because I'm looking for a null hypothesis from you guys here. Start with your null hypothesis, please, and state that. You're going to say my null hypothesis is this, and my alternate hypothesis is the opposite. So this is bad because that was not specified here. The null hypothesis is that there's no difference in reduction in the sensation of hunger between sugar and potato chips or anything. So that's bad. You can revise this hypothesis and it would be perfectly good, and that'd be a pretty cool experiment to do. All right. Here are some potential test questions regarding null and alternative hypotheses, including the ones I just gave you. I think that changing temperatures affect lettuce seed germination. My null hypothesis is temperature affects let us see germination. Is this okay? No, it's not, because the null hypothesis is also a statement of no effect. So a good null hypothesis would be that temperature has no effect on let us see germination. Is this a good null hypothesis? Men are worse drivers than women. Not a null hypothesis. The null hypothesis would be there's no difference in their driving. That's one reason why that's a bad hypothesis. Is this a good null hypothesis? Men drive faster than women on Highway 101 between Arcata and Eureka. Oh yeah, because like how do you measure worse drivers? I mean, give me more information on that by having more accidents, or I don't know. How about this one? Men drive faster than women on Highway 101. Well, maybe you could measure that, but it's not a null hypothesis. The null hypothesis would be there's no difference in how fast the two drive. So that's a bad one. How about this? My null hypothesis is that there is no difference in how fast men and women drive between Arcata and Eureka. That's pretty good, except I wonder how you would measure that. What are you going to do? You're going to tailgate people, or I'm going to say that's hard to say. It is a null hypothesis. It might be testable. I don't know if you could test it safely. I'm inclined to say bad, but that's borderline. Maybe, yeah. At least I'm consistent when I make these PowerPoints and when I deliver them. Okay. So here we go. That's it. Check the due date for your first science assignment and any other additional instructions there. Just check that stuff. I haven't said everything here. So hopefully I've gotten you started, but there will be more there. Get it done. So, and try to have some fun with it. Okay, ciao.